Welcome to our session on magnetism, magnons, quantum magnetism, and spinons. So today we are going to focus on magnetism, and in particular, we are going to have the following learning outcomes. We will show how magnetism appears in minimal models having hopping and electronic interaction. We will see how, in the presence of these interactions, a symmetry broken state appears, and excitations around this symmetry broken state can be derived, which are in particular known as magnons. We will also see that if you have strong quantum fluctuations, you can actually have magnets that do not break time reversal symmetry, that are called quantum spin liquids, and we will see what are the excitations of these quantum spin liquids. And then finally, we will look at some model that it's dominated by quantum fluctuations, that it's called the Kondo lattice model, that it's also a magnetic system that it's characterized by not breaking time reversal symmetry. So to focus on a very specific type of materials, let us first think about what are the different types of magnets that we are going to discuss today. So there are two big classes of magnetic systems that we are going to analyze. The first class of magnetic systems are magnets that break time reversal symmetry. These are materials that have a net magnetization, at least in each side, and this net magnetization is equivalent to a spin angular momenta, and therefore having a finite spin angular momenta breaks time reversal symmetry. You can think that all conventional magnets belong to this class, like ferromagnets, antiferromagnets, even non-collinear magnets correspond to systems that break time reversal symmetry. And then we can have a very specific type of magnets that they do not break time reversal symmetry, or they do not necessarily break time reversal symmetry in the classical way, and these are called quantum spin liquids. These are systems that have local spins on each side, but that the spins are fluctuating in a quantum mechanical way, and the net ground state is a ground state that has a massive entanglement and that we need to describe using quantum many-body physics. In order to think about specific materials that belong to these classes, let us bring up a few examples. So in the set of magnets and antiferromagnets, you can think that most of the conventional magnetic materials are found in that class. And in particular, let's say iron is a very conventional ferromagnet, and antiferromagnets like, for example, nickel oxide or many other transition metal oxides also belong to the class of materials that are known as antiferromagnets. Then we have also real materials that belong to the class of quantum spin liquids. And one very popular one is herbensmithitite, that it's a very complex material that features a Kagome lattice of local magnetic moments. And among the magnets that do not break time reversal symmetry, we also have systems known as Kondo lattice models, and in particular, these systems are characterized by having a lattice of local magnetic moments coupled to a metallic electron bath. And one of the examples of these materials are rare earth compounds. And in particular, samarium hexaborate is a very well-known heavy fermion insulator that realizes a Kondo lattice model. Today, we are going to focus on two different types of excitations that appear in magnets, both in magnets that break time reversal symmetry and magnets that do not break time reversal symmetry. If we think first about magnets that break time reversal symmetry, we have that these materials feature a very specific type of excitation known as a magnon. This is a fluctuation of the magnetic moment. You can think that a ferromagnet has a net magnetic moment, and just the fluctuations of that order parameter corresponds to magnons. You can think that it's the magnetic analog of a phonon in a crystal. Magnons are emergent quasi-particles in the material. What this actually means is that they are, of course, made of electrons, but their properties are completely different from the properties of electrons. And in particular, magnons have spin 1 in comparison with spin 1/2 of electrons. And what is most important is that they do not have any charge. So magnons have charge equal to 0, and they are not affected by electric fields. What this actually means is that you can actually have materials that are insulators from an electronic point of view, namely that if you try to apply a current, you don't have a massive resistance and electrons cannot propagate, but magnons can actually propagate. And this is the case, for example, of ferromagnetic insulators. Then, if we focus on the types of materials that do not break time reversal symmetry, and in particular quantum spin liquids, then in those systems we have a completely different type of excitation. It is still an emergent excitation, meaning that it is made of electrons, but it has properties completely different from electrons, but it's also different from magnons. And these excitations are called spinons. And one way of thinking about them is that spinon corresponds to 50% of an electron. Electrons have spin 1/2 and finite charge, but the spinons only have spin and no charge. And you can think that spinons also appear in materials that are effectively insulators, that are insulators thanks to strong correlations. So charge cannot propagate in this material whatsoever, but spin can still propagate in this material. And this is a different type of emergent excitation that does not exist in conventional magnets, breaking time reversal symmetry, but it appears in quantum magnets. The idea of magnetism is very much related with symmetry breaking. And this is something that we have discussed also in the previous sessions of the course. So you can think that when you have a Hamiltonian with many body interactions, those interactions may spontaneously break some symmetry in the ground state that is present in the Hamiltonian. In the case of conventional magnets, meaning magnets that break time reversal symmetry, the symmetry that is broken is either time reversal symmetry or spin rotation symmetry in real space, meaning that your system has a net magnetization in a very specific direction. Of course, if you have a configuration with all spin up, there's another configuration with all spin down that has exactly the same energy, but the material is going to choose one of the configurations in the experiment. And this, of course, just one specific example of symmetry breaking. There are other examples of spontaneous symmetry breaking, like charge density waves. These are essentially systems that have a charge arrangement that breaks the original lattice symmetry of the system. So let's say translational symmetry is spontaneously broken. And of course, we also have the case of superconductors, in which case the symmetry that gets broken is gauge symmetry, which is essentially this transformation in the creation and annihilation operator that adds a phase, and the superconducting order essentially breaks that symmetry. So all these three states can be understood from a many-body Hamiltonian that has kinetic energy and that has many-body interactions. This kinetic energy is conventional hopping of electrons. It's the term in the Hamiltonian that we can easily solve either analytically or numerically. And if we only have this term, we say that our Hamiltonian is a single particle Hamiltonian. Once you add this term, that corresponds to a biquadratic interaction between fermions that you can think as a density-density interaction, for example, then Hamiltonians become much more difficult, and in general, we cannot find an exact solution. There's, of course, a trick for this, which is using mean field theory. And when you do mean field over this Hamiltonian, you can find solutions that break specific symmetries that this Hamiltonian has. You may break time reversal symmetry, you may break translational symmetry, you may break gauge symmetry. And so the idea is that depending on the details of this interaction term in the Hamiltonian, we may have completely different types of ground states. We may have magnets, we may have charge density waves, we may have superconductors. And of course, these interactions can arise from many different sources. You may have contributions to this biquadratic interaction that come from electrostatic interactions. These are classical let's say, interactions that are of the form density-density that arise due to the finite charge of electrons. But then you can also have interactions that are mediated by other quasi-particles. You can think that, for example, phonons in a material may mediate interactions between electrons. You can think that quasi-particles such as magnons and plasmons may also mediate interactions between electrons. What is important is that if you want to have magnetism, you need to have some net interaction that is repulsive, which is relatively easy because electrostatic electron-electron interactions are repulsive. So if classical electrostatic wins, then magnetism easily arises. And that's one reason why magnets are, let's say, relatively common in nature. The idea to understand the emergence of magnetism can be summarized in this very simple Hamiltonian. So you can have a Hamiltonian that corresponds to, for example, a one-dimensional tie-bonding model with first neighbor hopping, and then you add interactions in the simplest form that you can imagine. For example, a local density interaction. So C dagger up, C dagger down, C down. And this local interaction is what is called the Hubbard term. And depending on the sign of U, you may have a ground state that is superconducting, in the case of negative U, which is attractive interactions, or you may have a ground state featuring magnetism that appears when you have positive U, namely repulsive interactions. Today, we are going to focus on this case with positive U. So the previous Hamiltonian is, of course, let's say, very hard to solve, and in practice, it is impossible. So we need to use our mean field approximation. And the idea of the mean field approximation is that you can start with the challenging term in your Hamiltonian, which was the bilinear, the biquadratic term in the Hamiltonian that had 4 fermionic operators. And you can decompose this biquadratic term into 2 terms that are bilinear. And in particular, the only trick is to start taking expectation values between 2 of these operators. So for example, you can take expectation value between C dagger up, C up, which is what we do here on the right. And then you would have the other term that is expectation value of C dagger down, C down. Now, this expectation value is effectively a number. What this means is that you transform a Hamiltonian that is biquadratic onto a Hamiltonian that is just bilinear. But something very important to notice is that the expectation value C dagger up, C up, doesn't have to be necessarily the same as C dagger down, C down. And if you have different expectation values for these 2 operators, what you actually have is a system that has more up electrons than down electrons. Because if you recall, this term over here counts the total number of up electrons that you have, and this term over there counts the total number of down electrons that the system has. So in a way, the difference between these 2 values is how many more up electrons you have in comparison with down electrons. A magnet is just a system in which this expectation value is different from 0. And from a self-consistent point of view, if you have repulsive U, namely U bigger than 0, then you can get to a self-consistent solution where these 2 values are different. And this difference is what we call the exchange field, that it's in a way a measurement of how many up electrons you have in comparison with down electrons. And effectively, the net Hamiltonian that you end up with is something like this. So M sigma C, where sigma C is spin Pauli matrix, and then the creation and annihilation operators. What is important to note is that in this mean field Hamiltonian, we can make many different choices. So before, we made the choice of taking expectation value of C dagger up, C up, and C dagger down, C down, but we could also make the choice of taking expectation values between C dagger up and C down. When we do that, we also get a bilinear term in our Hamiltonian, but it's different from the one that we considered before. And in particular, depending on which expectation values you take, either C dagger C up or C dagger down, C down, you will be describing a magnet that has magnetization in the C direction, or a magnet that has magnetization in the X or Y directions. So from a mean field, you can actually get both magnets that have magnetization in the C direction or in any possible direction in space, and in particular, in a non-collinear way. Okay, so something very important to note is that mean field is valid when we have relatively weak interactions, namely when U is much smaller than T. But today we are also going to focus on the case where the interactions are very strong, which is the case where U is much bigger than T. We will see that in that situation, we actually need to do a different approximation. So we cannot only do mean field, but we need to do something else. And what it's important to note is that this limit of very strong interactions is very often the limit in which many materials actually are. But to understand what is the nature of this state, let us start with the case where we assume that we can actually use mean field. So we are going to take our tie-binding Hamiltonian with first neighbor hopping, for example. So we are going to consider that we have just a one-dimensional tie-binding chain. We add our interaction term, that it's repulsive. We do mean field, assuming that mean field works. And of course, we need to assume that there's a certain amount of electrons in the system. And for this calculation, we are going to assume that we have 20% of the electrons present. So 20% of the maximum number of electrons that we could put in the system. If you take this Hamiltonian, you apply mean field and you solve it self-consistently, you will see that the resulting band structure looks like this one on the right. And now in the band structure, what you can see is that we have the electrons for the up channel that are colored in blue, and then we have the electrons for the red channel that are for the down channel that are colored in red. And the chemical potential is located at 0 energy. So now if you count how many electrons up you have in comparison with down, you see that you only have up electrons occupied, and then the down electrons are completely empty. What this actually means is that you have an imbalance between the number of electrons. You have a net magnetization because you are filling more up electrons in comparison to down electrons. And something important to notice in the band structure is that there's a splitting between the bands, that it's actually associated to that different number of electrons. And this splitting in the bands is what we call the exchange splitting, and it's driven by interactions. So the stronger the interactions, the bigger this splitting is. Let us continue with this one-dimensional tie-binding model. So before we considered that we had a filling of 20% and we chose a unit cell with a single site. But of course, we can make different choices. We could choose having a unit cell with two sites, namely that we enforce that our system has translational symmetry when we move the system, let's say, by two sites. And what we are going to do now is we are going to solve this model in the presence of interactions, but at half filling. It is first interesting to look at how the band structure looks like in the absence of interaction. So this is the case of U equal to 0, and what you actually see is that you have two bands, because of course you have two atoms per unit cell, and these bands cross at one point, and the system is of course metallic. Once you introduce interactions, what actually happens is that a gap opens up due to the mean field Hamiltonian. Opening a gap is usually good in terms of energy because you decrease the value of the occupied single particle eigenenergies. And if you look at what happens in real space when you introduce interactions, what you actually see is that an antiferromagnetic order appears. So you have in one side more up electrons and on the other side more down electrons. So the net magnetization of the system is 0, but every single side is magnetized in an opposite direction. Of course, you could have made this calculation with a unit cell with a single site, and in that case, you would have ended up in a ferromagnetic configuration. And now you could ask yourself, well, hold on, I can actually solve the very same problem using two different guesses. I could look for a solution that is fully ferromagnetic, and this is a self-consistent solution. So you can actually do the numerical calculation, you can converge it, and then you could also get to a different solution, which is the antiferromagnetic one, that is also a self-consistent solution, and that you can also converge it. So now the question is, well, which one of these two solutions is the correct one? Because of course, these two solutions are physically different. One has a net magnetization, the other doesn't have a net magnetization, and only one of them must be correct. In order to know which configuration is correct, the only thing that we need to do is to compare the energies. So the ground state is going to be the state that has the lowest energy. And in particular, just by looking at the eigenenergies observed in the band structure, you can already infer which one is going to have the lowest energy. So the ferromagnetic state is actually metallic, right? There's no gap opening whatsoever, whereas the antiferromagnetic state is an insulator. It's an insulator with a relatively strong gap, And there's actually many states that have almost the lowest possible energy. So when you compute the total electronic energy of the system, what you are going to observe is that the system that has a gap has a lower total energy than the system that does not have a gap. And now you can ask yourself, well, how does this energy difference evolve as you go from weak interactions to much stronger interactions? And let us start with already a relatively sizable interaction. So with interaction equal to 20. So if you start increasing the interaction, what you actually see is that as the interaction becomes stronger and stronger, the energy difference between ferromagnetic configuration and antiferromagnetic configuration becomes smaller and smaller. So in the limit of infinite interactions, which is the same as the limit where the kinetic energy is 0, the ferromagnetic and the antiferromagnetic configurations have the same energy. But then if you go to a more modest interaction, then the energy difference becomes bigger. And of course, once you go to U equal to 0, you must have a 0 energy difference between both configurations. Something very interesting to notice is that you can actually fit this energy difference with a functional form of 1 over U. And this is something that we are going to derive more explicitly later on in the strongly correlated limit. At this stage, what it's important to note is that the antiferromagnetic configuration has lower energy and that the energy difference goes as 1 over U. Okay, so now one important question is, what do we need in order to have magnetism? Is it enough to have any finite interaction? Do we need a critical value of the interaction? Do we need a very specific electronic dispersion? What are the conditions in order to have, let's say, a net magnetic moment? So one way of getting a criteria for magnetism is through perturbation theory. And in particular, we can actually demonstrate that magnetism is going to appear if you have a product of the interaction strength times the density of states that it's bigger than 1. What this actually means is that if your interaction is very strong, or if your density of states is very big, it is very easy to get magnetism. In contrast, if your interaction is very weak, or if your density of states is very weak, then it is very hard to have magnetism. And what is most important is that if you are below this criteria, then magnetism does not appear. This is the reason why we have metals that are non-magnetic, because those metals essentially are below this criteria. So if you think about aluminum or lead or any other non-magnetic metal, then of course we are going to have finite interactions, we are going to have finite density of states, but if this product is smaller than 1, then magnetism does not appear. In contrast, if you have a metal that has a large density of states, a sizable interaction, then magnetism is going to appear, and that is what happens, for example, in iron, in cobalt, in many other magnets. This criteria is something that one can, let's say, very easily demonstrate numerically. So you can take, for example, a one-dimensional tie-bending model, and you can start computing the self-consistent magnetization as a function of the interaction. And what you can actually observe is that if you don't have any interaction whatsoever, of course, there's no magnetization. Once you add some interaction, but not strong enough, then you still don't have magnetization. But once you go above a critical value, then you start having a magnetization. And this magnetization becomes bigger and bigger and bigger as you increase the value of the electrostatic repulsion. So magnetism requires a minimum value of the electronic interaction. And once you go above that value, then your magnetic moment becomes stronger and stronger. Okay, so magnetism often requires having very large electronic interactions usually much stronger than the hopping. And that is exactly the regime where mean field theory actually breaks down. So one important question is, how can we understand magnets? if the technique that we have breaks down in the regime where magnetism often appears. And that is what we are going to address right now. So we are going to address the so-called strongly localized limit, which is a limit in the electronic model that allows us to map the electronic model to a spin model that is known as a Heisenberg model. And let us start with the one-dimensional chain. So the one-dimensional chain at half filling, where the ground state was effectively an antiferromagnetic state. In this system, you can start, for example, asking yourself, what is the value of the magnetization as I increase the value of U? So if U is equal to 0, you don't have any interactions, and therefore the magnetization must be 0. And then as you increase U, your magnetization per site slowly starts increasing, and eventually at very large U, it saturates to the maximum value that is 1 Bohr magneton. This actually means that for very large U, you have exactly spin 1/2 in each site. Of course, they are pointing in opposite directions, and you effectively have one localized electron in each site that gives rise to that local magnetic moment. So at strong interactions, electrons do not actually move. You actually have a spin 1/2 electron that is localized in this site, another electron that is localized on the other side, and they cannot jump around because jumping would be too energy costly. What that actually means is that we should start thinking about the ground state of our system not from the perspective of kinetic energy, but actually from the perspective of localization. And what this actually means is that the good starting point to understand the physics of the system is a starting point where electrons are localized in each system, and then the hopping or the kinetic energy is actually a perturbation around this ground state. And to understand this point, let us look at a simplified model. So let's imagine that we have one model where we just have two sites, site number 0 and site number 1. And in each site, we have spin up and spin down. So the Hamiltonian that we are going to consider is a Hamiltonian that has kinetic energy. So electrons can jump from site 0 to site 1. And then we have some local repulsion. So we have repulsion in site number 0, and we have repulsion in site number 1. And now, if you think about the system at half filling, meaning that we have in total 2 electrons, you can easily figure out that there are in total 6 potential states for our system. We can either have electron up in first site and up in the second site, down and up, down and down, up and down, or the 2 electrons on the same side, namely the second or the first one. And these are all the configurations at half filling. And now the question is, well, how can we define a low energy manifold for this Hamiltonian, and how we can define a high energy manifold? And once we define those two manifolds, how can we come up with a low energy Hamiltonian that allows us to describe the dynamics of these low energy degrees of freedom? In the limit where interactions are very, very strong, namely the limit where on-site interaction U is much, much bigger than T, then what we have is that some of the states have an energy that is roughly the same, and we can set to 0, and other states have an energy that is very large, that is proportional to U. In particular, if electrons are in different sites, then we don't have to pay any interaction energy, whereas if electrons are on the same site, then we need to pay the charging energy U. So this allows us to define a low energy manifold and a high energy manifold. And what we have to do now is to use these two sets of states to define a Hamiltonian that allows us to describe the dynamics of this low energy manifold. So what we actually realize first is that the low energy manifold is composed of states that have exactly 1 electron per site, and that the spin of this electron can be either up or down. In other words, the charge degree of freedom is completely frozen. The low energy manifold always has charge 1 in each site, and no matter which state you choose, you always have charge 1. Whereas the spin can still fluctuate. You can go from this state that has up, up to the state that has down, up. So the dynamical degrees of freedom are just the spin, whereas charge is no longer there. So what we need to do is actually to write down a Hamiltonian for this spin degree of freedom alone, ignoring the charge degree of freedom. And the way we do this is by writing the simplest Hamiltonian that involves only the spin degree of freedom, which is the Heisenberg Hamiltonian. So we have the spin inside 0 that we call S0, and then we have the spin inside 1 that we call S1. And these two spins must be coupled because that's essentially what is going to govern the dynamics. And this scalar product guarantees that the coupling respects rotational symmetry. Now the question is, how are we going to extract the J from the electronic model? So what is going to be the relationship between the hopping in the electronic model, the interaction in the electronic model, and the J in the effective spin model? The way we extract this J is just by doing perturbation theory. And in particular, to do perturbation theory, we need to make two choices. We need to make the choice of what is H0, namely the pristine Hamiltonian. So this is the Hamiltonian for which we know the eigenstates. And then we need to make the choice of who's going to be the perturbation. This is essentially the term in the Hamiltonian that mixes the low energy manifold with the high energy manifold. And as we've discussed below, when we are in the strongly correlated limit, namely the localized limit, it is natural to choose as the pristine Hamiltonian the Hubbard term, because this is the term that has a low energy manifold with exactly 1 electron per site, and then as perturbation, the hopping itself. So the hopping allows you to go from states that have 1 electron per site to states that have 2 electrons on one side and 0 electrons in the other side. And now, if you apply the formula of second order perturbation theory that essentially involves matrix elements between the grounded state and the excited state, then what you actually end up is that the value of J is proportional to T squared over U, where T essentially comes from this matrix element between the low energy manifold and the high energy manifold, and then U comes from the energy difference between your grounded state manifold and your high energy manifold. And now you can very easily recognize that the difference between a ferromagnetic configuration and an antiferromagnetic configuration is essentially proportional to J. And when we were doing mean field, we obtained that that energy difference was proportional to 1 over U, which is exactly the same difference that you obtain over here. So in a way, mean field predicts the correct dependence on of the difference between ferromagnetic and antiferromagnetic as what we obtain when we do an actual many-body calculation. Okay, so now the previous argument can be used systematically for any lattice at half filling. So instead of considering two sides, let us now consider that we have one lattice that can be triangular, it can be square, it can be Kagome, but what is important is that we actually have a set of hoppings between sites I and sites J, and then apart from that, we have our local on-site interaction inside I. You can now use the very same procedure as before for every single pair ij, and what you obtain is that in the limit in which u is much, much bigger than t, you can transform this electronic Hamiltonian onto the Hamiltonian of a spin model, where the different couplings jij are just given by the hopping tij to the second power over u. And this is something that one can systematically extract for any tie-bonding model just by following the same procedure as the one that we did before for every single pair ij. Now, if we think more generically in terms of Heisenberg models, we can think that these constants jij can be classified in two big classes. So we can have constants that are positive. Those constants that are positive promote states that have opposite alignment between the spin I and spin J, because of course the grounded state of this Hamiltonian is going to be the state with the most negative energy. And then we could have also Hamiltonians where these Jij's are negative. And when Jij is negative, the state that minimizes the energy is a state that has magnetization pointing in the same direction. And this is what we call ferromagnetic coupling. Apart from having spin Hamiltonians with these JIJs, there can be other spin Hamiltonians with more exotic interactions. In particular, there can be interactions between any spin component inside I, for example, Sx, and any spin component inside J, for example, Sy. These types of interactions appear especially when you have spin-orbit coupling terms, where you have terms in your kinetic energy that break the spin rotational symmetry. They are going to be very important in the case of quantum spin liquids, for example. Okay, so if we now look at the Heisenberg model, namely the model that has only two sides, we can understand very easily two different ground states. So the ground state where Jij is bigger than 0 has essentially an antiferromagnetic arrangement. This is the arrangement that minimizes the energy, whereas the configuration with Jij smaller than 0 has a ground state arrangement with the spins pointing in the same direction, and this is what we call the ferromagnetic ground state. This is from a classical point of view. This happens if we consider that the S in the Hamiltonian are just classical vectors. If we now look at a fermionic Hamiltonian that we solve with mean field theory, we can very easily see those different types of arrangements. So for example, if we look at a model that is bipartite, for example, a square lattice or a honeycomb lattice, and we take that in this model, we have a tie-bonding model, we have in Tij and some local interactions, we can very easily obtain the antiferromagnetic configuration. So we can solve this model at the mean field level, which is what it's shown in these pictures, and you observe that the states in one sublattice have spin pointing in one direction, and the states in the other sublattice have state pointing in the other direction. The reason for this can be very easily understood from the Heisenberg model, namely this model in the limit of large U can be mapped to a Heisenberg model, and that Heisenberg model has antiferromagnetic interactions that lead to a grounded state like the one over here. However, you could also choose other different types of lattices. You could have chosen lattices that are not bipartite, meaning that you cannot assign some sides to sublattice A and other sides to sublattice B. These models are, for example, the Kagome lattice models or triangular lattice models. In these cases, we still have antiferromagnetic correlation, so spins still want to point in opposite directions in Nick-Borin sites. However, since the lattice is not bipartite, there's no arrangement that allows you to have antiferromagnetism between all the neighbors. So the system chooses the next best solution, which is having a non-collinear magnetization so that the amount of antiferromagnetism between neighbors is maximized. This is something that naturally happens if you have a lattice that is not bipartite, that it is usually called a frustrated lattice, and interactions in frustrated lattices very often give rise to non-collinear magnetization. Now, there's one point that we need to discuss still, which is the case of ferromagnetic coupling. From the point of view of perturbation theory, when we were deriving the exchange coupling as a function of the hopping, we actually obtained that the exchange coupling was proportional to t² over u, namely that it was always positive, which means antiferromagnetic. But there are materials that have ferromagnetic coupling. So an important question is, how does this ferromagnetism appear? The answer to this is that to get ferromagnetism, one often needs to involve intermediate orbitals, and this is what it's usually called super exchange interaction, and in particular it can be understood in a relatively easy way. So let us imagine that we have, let's say, two different transition metal atoms, which are the atoms that have the actual magnetic moment. This can be cobalt, iron, nickel, and so forth. And now in between these two atoms, you actually have a third atom that is a ligand. That can be, for example, oxygen. You could think that the electrons jump from this atom to this atom, and this would give rise to some antiferromagnetic configuration, but electrons may also decide to do something else. They may decide to jump from this side to the side over here, and from this side to the side over there, so that there's a virtual state with two electrons, like this, And now you can ask yourself, well, what is the correction to the energy that this virtual state creates in the ground state? And in certain cases, depending on the orbitals that you have, this correction may allow the ferromagnetic state to have lower energy than the antiferromagnetic state. And in those situations, your net exchange coupling is going to be ferromagnetic. This is something that has been worked out some time ago, and it's known as the good enough Kanamori rules. And this is something that one can systematically obtain just by doing self-consistent calculations in multi-orbital models, for example, with density functional theory. We also discussed that there are other terms in the Hamiltonian that are not isotropic, that they arise when we have strong spin-orbit coupling interactions. And there are three different terms that are relatively easy to understand. So let us look first at this term over here. So this is essentially a cross product between spins. So Heisenberg model is usually with a scalar product, but we could also think about doing a cross product between them. And of course, we need to do a scalar product with some other vector. This type of term in the Hamiltonian explicitly breaks mirror symmetry in the Hamiltonian. And in particular, thanks to this cross product, it sort of promotes magnetic configurations where the spins actually have a 90-degree rotation. This type of, let's say, spin interaction promotes non-collinear order thanks to this spin rotation, and it appears when you have systems on top of a surface, because the surface breaks mirror symmetry, and it's called antisymmetric exchange. There are other types of interactions that are more similar to the Heisenberg term, but they only involve one of the spin components. So you can think, for example, about SCI, SCJ. This type of interaction is what is called an isotropic exchange or Ising interaction, and this essentially promotes an easy axis of the magnetization. So this allows the system to have magnetization more easily in the out-of-plane direction than in the plane or the other way around. And then there's another interaction that it's called the Kitev interaction, that it's an interaction that is relatively similar to the anisotropic exchange, but that it's bond dependent. So along one of the bonds, you have an SC-SC interaction. Along other bond, you have SX-SX, and along the other bond, you have SY-SY. And of course, it is very easy to figure out that this interaction alone promotes frustration. So you can think that having a non-bipartite lattice promotes frustration, and also having this type of interaction in a bipartite lattice also promotes frustration. And this is an interaction that is very important for quantum spin liquids. Okay, so up to now, we have focused on the ground state of the Hamiltonian, meaning that we took an electronic model and we studied what was the lowest energy state of this model. Now let us look at excited states. And to understand excited states, we actually need to involve quasi-particles. In particular, let us focus first on the simplest type of quasi-particle, which is the case of a magnon. That is a quasi-particle that appears in a ferromagnet. A magnon is essentially a fluctuation of the order parameter. You can think that a ferromagnet is a system that has a net magnetization pointing one direction, and now if you inject a little bit of energy in the system, you may create small fluctuations of this magnetization, and these fluctuations can propagate in space and effectively behave as a quasi-particle, and this is what we know as a magnon. There's a relatively systematic way of extracting magnons for quantum material that essentially relies on starting with a Heisenberg model. So we are going to take our model that has exchange interactions Jij and local spins, and we are now going to treat these spins as quantum mechanical operators. What this actually means is that spin operators are going to have commutation relations following the conventional angular momenta, and these spins are going to be associated to a spin 1/2, spin 1, spin 3/2, or spin 2, or even higher. And the question that we want to ask ourselves is, what is the simplest way of finding the low-lying excited states with respect to the ground state? To do this, let us first start with the ground state. So the ground state of this system is relatively easy to write down, especially in the case of ferromagnetic interactions. So if interactions are smaller than 0. The state that minimizes the energy is the state with all the electrons up. That is the state that we call up, 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 up. And now this is going to be our ground state. And what we want to do is we want to look at states that are very close in energy to this state. And that in particular are the states that host the magnons or the one-to-many body excitations. To do this, we actually use just a relatively simple trick. And the trick consists on doing just a mathematical mapping between spin operators and bosonic operators. So this is just a mapping between two Hilbert spaces. And although the mapping may look a little bit complicated, it is actually relatively easy to understand. So the mapping is called Holstein-Primakov transformation, and it's a transformation that allows you to go from a spin operator to a bosonic operator. And what it's important to note is that this sort of transformation is mathematically exact, meaning that if you put this definition in the algebra of the commutation relations of the spin operators, you see that having bosonic operators automatically fulfills that algebra. So in principle, you're actually describing the same Hilbert space. Of course, this if we use this mapping, it may seem that the Hamiltonian becomes more complicated than what it was before. But the actual trick is that we can simplify this mapping in the limit in which that it's relevant for magnons. So the idea is that if we assume that the expectation value of these bosonic operators is very small, and in particular is much smaller than S, then calculations simplify substantially. And what is important to note is that assuming that this expectation value is very small is the same as assuming that the expectation value of SC is the same as the magnetization, meaning that we assume that we are on a state that is very, very close to the ground state. What that means is that our magnetization is almost as big as it could be. And this is, of course, the regime that we want to target. So the idea is that if you assume that this expectation value is very small, you can, let's say, take that this term over here is going to be 0, and this term over here is going to be 0. So effectively, S plus is proportional to A, and S minus is proportional to A dagger. And now you can just take these definitions and put them inside your Hamiltonian. And by doing the replacement, you transform a Hamiltonian that it's originally written for spin operators onto a Hamiltonian that it's written in terms of bosonic operators. And what is important to note is that the hopping in this Hamiltonian for bosonic operators is proportional to the exchange coupling that you had for the original Heisenberg model. So in short, in order to extract magnons of a Heisenberg model, we need to do the following mapping. The S plus operator becomes the destruction operator of the magnons. What this actually means is that increasing the spin of the system is destroying a magnon. S minus becomes the creation of a magnon. What this actually means is that decreasing the magnetization of the system creates a magnon. And finally, the total magnetization of the system is the maximal magnetization minus the number of magnons. The physical interpretation of this is that every time that you have a magnon in the system, you are decreasing the total magnetization of your system. So if you look at what is the actual spin of your magnons, what you actually see is that magnons are spin 1 excitations, that they exist thanks to the spontaneous symmetry breaking. Again, this approximation is valid because this expectation value is very small. So now, once you have a tie-bonding model for magnons, you can actually have many different dispersions for your magnons. You can actually have magnons that are gapless, meaning that they can have energies as close to 0 as you wish. You can also have magnons that have a finite gap, and you can also have magnons that have a Dirac-like dispersion. What is important to note is that these types of magnons that are quadratic appear mostly in ferromagnets, whereas magnons that have a linear dispersion appear mostly in antiferromagnets. And of course, if you have electronic dispersion for magnons or a relationship between momentum and the energy, you can also have topological bond structures for magnons. And this is what happens, for example, if you have, apart from the Heisenberg coupling, some strong spin orbit coupling in the system. And in particular, you can have magnon electronic structures that have a certain spectral gap, but that this spectral gap is actually topological and it has a finite Chern number. And therefore, when you look at a ribbon, you essentially have chiral edge states associated to magnons. These are spin 1 excitations that are topological, and they arise thanks to the existence of a non-trivial topological invariant in the magnon Hamiltonian. Okay, so up to now we focused on systems that break time reversal symmetry. But there are magnets that do not break time reversal symmetry. And this is the case of quantum spin liquids, and they have something very special, which is the emergence of a completely different type of excitation, which is a spinon. So to understand quantum spin liquids, it is good to make a step back and start with the simplest model for a magnet. And in particular, if we consider that we have two sites, we can focus on the so-called Ising dimer. This is a Hamiltonian that looks like SC0, SC1. So it only has coupling in the C direction. And if you look at this Hamiltonian, you can actually notice that there are two ground states that you can write down. So there's the ground state with up-down, and there's the ground state with down-up. These two ground states are what we call classical ground states. They can be described as a product state, and they do not have any quantum entanglement whatsoever. And what's important that each one of them breaks time reversal symmetry. Of course, this one is the time reversal symmetric of this other one, but the system is going to choose essentially one of these. And you can think that a conventional macroscopic ferromagnet is just a version of this with an infinite number of sides. But now, if you look at the Heisenberg model of a dimer, you can actually realize that the ground state of the Heisenberg model is completely different. And in particular, if you treat S0 and S1 as quantum mechanical operators, what you actually obtain is that the lowest energy state is not up-down, but it's actually a linear combination between up-down and down-up. And in particular, is the so-called singlet state. What is important is that this ground state is singly degenerate. There's one and only one state that has the lowest energy. This state is also time reversal symmetric, meaning that it has no net magnetization, and when you apply time reversal symmetry, you get the very same state. And third, it is a state that is maximally entangled. A quantum spin liquid is just a macroscopic system that features this type of wave function. So you have entanglement between all pairs of spins, and this happens at a macroscopic level, and the expectation value of the spin on every single side is 0. When you define quantum spin liquids in this way, you very quickly realize that the mean field theory that we used for electrons is not capable of capturing quantum spin liquids. So the conventional Hartree-Fock method does not allow you to predict which systems are going to have a quantum spin liquid behavior, because by definition, mean field breaks time reversal symmetry. So the question is, well, how can we understand quantum spin liquids and when they can arise? So let us start with when they can arise. So we previously discussed that we can have magnets that have magnetization in the same direction that we call ferromagnets, or magnetization in the opposite direction that are called antiferromagnets. Or in some cases, if we have geometric frustration, we can have something in the middle, which is with magnetization not perfectly ferromagnetic and not perfectly ferromagnetic, which is what we call frustrated magnetism. Quantum magnets appear if you have a frustrated magnet that has strong quantum fluctuations. So quantum fluctuations essentially disorder all these spins and give rise to a ground state that has a net zero magnetization and that it has long range entanglement. And in particular, this is something that very easily happens in triangular lattices and Kagome lattices. So if you take an antiferromagnetic Heisenberg model in a lattice that is non-bipartite, there's a possibility of having a ground state that is a quantum spin liquid state. Okay, so writing the wave function of a quantum spin liquid is actually very hard. So what we actually want to do is to look at excitations over the ground state. And to do this, we are going to use a relatively simple trick. So let us imagine that we have a Hamiltonian that describes a quantum spin liquid, and we make the choice of exchange constants that guarantees that we are in a quantum spin liquid regime. In that regime, what we know is that the ground state must have 0 spin for every single site. And when you have 0 spin for every single site, you could ask yourself, what are the excitations around the ground state? The first solution that may come to your mind is to use the Holstein-Primakov transformation that we described before. But you very easily realize that that actually doesn't work. And the reason for that is relatively simple. So if you have a quantum spin liquid, the net magnetization is 0 in every single site. What that actually means is that if you look at the expectation value of SC, written in terms of the bosonic operators, you should have that S minus the expectation value of the number of bosons is 0. But this requires that the number of bosons is relatively large, and in particular large enough to compensate for this S over here, which is exactly the opposite condition for having magnons. So for having the mapping between Heisenberg model and our free bosonic model, we required that this expectation value was very small, so this is completely incompatible with having a quantum spin liquid. As a result, excitations in quantum spin liquids cannot be magnons. The approximation to obtain magnons completely breaks down. So the question is, what is the approximation that we can do in order to find the low energy excitations of a quantum spin liquid? And the answer to this is relatively simple. In a quantum spin liquid, we actually can think that we have local fermions that are trapped in terms of charge, but that they are not trapped in terms of spin. And one way of represent this is by so-called auxiliary fermions that are known as Abrikosov fermions. So we can say that every single spin is represented by a fermionic field that we call F. This F is not an electron, because remember, the charge of the electron is completely frozen, but it's just the spin of the electron. And you can now think that you can transform your Hamiltonian, written in terms of spin operators, onto a Hamiltonian written in terms of these spinon operators that are called as auxiliary fermions. But to do that, you must notice that when you transform a spin Hamiltonian into a fermionic Hamiltonian, you are introducing artificial degrees of freedom. And in particular, spins can be up and down, but fermions can be up, down, filled, or unfilled. And therefore, you need to restrict the Hilbert space of these artificial fermions. And the way in which you restrict the Hilbert space is by imposing the constraint that you must have one and only one fermion per site. If you do this mapping between spin operators and fermionic operators and impose this constraint on the fermionic operators, then you have an exact mapping between a Heisenberg model and an interacting fermionic model. So when you put those constraints, you can essentially go from your Heisenberg model written in terms of spin operators onto a Hamiltonian that is written in terms of these Abrikosov fermions that we call spinons. And in particular, you can replace each S by 2 fermions that give rise to a Hamiltonian that is biquadratic in fermionic operators. That Hamiltonian that is biquadratic in fermionic operators can be solved at the mean field level by taking expectation values, and that allows you to go to a Hamiltonian that is bilinear. And in particular, this Hamiltonian that is bilinear has some effective hoppings that are proportional to expectation values of the field operators. And in total, we have a tie-binding Hamiltonian for our spinon operators. And of course, we do this by enforcing time reversal symmetry all the time. So we have a Heisenberg Hamiltonian. We assume that the ground state has time reversal symmetry. We do the whole mean field in the spinon operators enforcing time reversal symmetry, and we end up with a Hamiltonian that has time reversal symmetry. So at the end, we actually find that the excitations of a quantum spinel liquid are actually described by some emergent fermions that have spin 1/2 and no charge. And these are what are called spinons. And now these spinons, of course, they can have their own dispersion relation. So you may have spinons that are gapless, and this gives rise to what is called a gapless quantum spinel liquid. You may have spinons that have a gap, and this is what it's called a gapped quantum spinel liquid. And you may also have spinons that are Dirac-like, that are linear in momentum, and this is what it's called a Dirac spin liquid. And which type of spin liquid you have essentially depends on what are these chi-ij that essentially come from the mean field obtained when you do the replacement of spin operators by fermionic operators. Okay, so finally, let us move on to a different type of quantum magnet, which is the so-called Kondo lattice model. And to understand this type of quantum magnet, it is first interesting to look at the simplest quantum magnet that combines a magnetic impurity with a two-dimensional electron gas. And now the idea here is that you can have a system that has simultaneously a spin 1/2 and that it's coupled to a two-dimensional electron gas. You can think that this arises from putting an impurity in a two-dimensional electron gas. So the Hamiltonian of this system is relatively simple. You have kinetic energy for your two-dimensional electrons. So you have 3 electrons in 2 dimensions with hopping. And then to describe the interaction between your local magnetic moment and the two-dimensional electron gas, you essentially put something that looks like a Heisenberg coupling. So it is S dot S, spin of the local impurity times the spin of the two-dimensional electron gas around the impurity. This is what is called the Kondo Hamiltonian, and this is intrinsically a many-body system, as many-body as the Heisenberg model. And of course, the ground state can be very complicated, but if you assume that each spin essentially traps 1 electron, you can actually write down that the ground state Hamiltonian is just a singlet between the spin of the impurity that is represented with this big arrow and the spin of 1 electron in the conduction path, that it's an electron that is at a certain distance from the impurity, and this is where all the quantum entanglement in the ground state comes, and then the rest of the wave function is just a conventional single particle wave function for all the electrons left in the ground state. The trick of the Kondo lattice model is to understand which electron is actually screening this impurity. Is it an electron that is very far from the impurity? Is it an electron that is very close to the impurity? Is it something in the middle? But for us, let us just focus on the fact that there's going to be a singlet between the impurity and one of the electrons. What is important is that the ground state of this model is effectively a quantum magnet. It's a S equal to 0 state. So we have a local magnetic impurity, but the ground state of the system does not break time reversal symmetry. So in a way, it's a quantum magnet. And now we can try to play the same game in the case when instead of having a single magnetic impurity, we have a lattice of magnetic impurities. And when you have a lattice of magnetic impurities, you could imagine that each magnetic impurity is going to trap a different electron. So this magnetic impurity is going to form a singlet with some electron, this magnetic impurity with some other electron, and so forth. So overall, you're going to have singlets between one magnetic impurity and one electron, and another magnetic impurity, another electron, and so forth. Of course, those different electrons may be shared. So the electron that screens this impurity may actually be 30% of the electron that screens this other impurity. What this creates is a massive entanglement in the system. But what is important to note is that the ground state of the system is still going to be spin equal to 0. In particular, every single magnetic impurity is going to be screened, is going to form a singlet with some electron, but there's going to be a massive entanglement between all the different magnetic impurities. So the question is, well, how can we solve this problem? And you may have already noticed that this problem is relatively similar to the quantum spin liquid model that we described before. And the way of solving the problem follows that exact same spirit. So the idea is that you start with your Hamiltonian for the Kondo lattice system that has the kinetic energy for the conduction electrons and the exchange coupling between the conduction electrons in every single spin. And now you replace those spin operators by some auxiliary fermions, by some abricosov fermions that you can even call spinons, and you put a constraint on the Hilbert space of those abricosov fermions as we did before. Once you make the replacement of spin operators by those fermionic operators, you essentially end up with something that looks like an interaction term in your Hamiltonian. So you have the conventional kinetic energy of your two-dimensional electron gas plus what was originally the Kondo lattice coupling that now is a coupling between the real electrons and the abricosov fermions in a biquadratic way. You can now take this Hamiltonian that it's biquadratic and solve it using a mean field decoupling. So you take expectation value between these two operators and these two other operators, and you transform the Hamiltonian into a valid linear model. And when you do that, you essentially transform this term that was originally the Kondo coupling onto a term that essentially mixes your original electrons with the abricosov electrons. And this term is what it's called the Kondo hybridization. So let us try to see how this electronic structure looks like. So in the absence of Kondo coupling, so you can think that this is the limit where J is 0, you essentially have a dispersion for your two-dimensional electron gas that can be, for example, parabolic, and then a dispersion for your auxiliary electrons or auxiliary fermions that are spinons or abricosov fermions that are essentially a flat band because they don't have any dispersion in this Hamiltonian. Now, once you switch on the Kondo coupling, so once you switch on this gamma k, you essentially create a coupling between the real electrons and the abricosov fermions, and what this coupling creates is a gap opening at the chemical potential. In particular, having this lattice of magnetic impurities leading to a quantum magnet state, so a state that doesn't break the universal symmetry, that has total spin equal to 0, essentially transforms a metal into an insulator. And this is what is called a Kondo lattice insulator, a heavy fermion insulator. And of course, depending on the strength of your Kondo coupling, you see that the system goes from a situation that it's metallic to a situation that has a finite gap to a situation that has an even bigger gap. So the gap of the system is essentially proportional to the value of the Kondo coupling. And this is something that you can understand by doing this Abrikosov mean field theory with spinons. This is everything that I wanted to tell you today. And to summarize, please remember that magnetism arises from repulsive interactions, and that when we have magnetism, we actually can have new exciting quasi-particles. In particular, we can have magnons that are quasi-particles with spin 1, and that they arise when we have a magnet that breaks transversal symmetry. We can have spinons that are quasi-particles with spin 1 half, and they naturally arise when we have a magnet that does not break transversal symmetry, such as a quantum spin liquid, and that we can actually have also quantum magnets that combine local magnetic moments with electrons that give rise to a Kondo lattice insulator.